Hello, everyone. My name is Ramin Hasibi. I'm a PhD student at the University of Bergen. And today I'm going to be presenting our work titled A Graph Feature Autoencoder for the Prediction of Unobserved Node Features on Biological Networks. So the motivation for this work comes from an attempt to integrate biological networks and omics data sets that are available out there. So biological networks of genetic transcriptional networks, protein-protein interactions, or metabolic interactions usually summarize complex biological processes in the format of a graph or network, and their structure are informative of the biological functions that they're trying to represent. At the same time, there are a lot of omics data sets such as genomics, transcriptomics, proteomics, these are data sets that are captured by technologies to measure the variation or activity of the genes or proteins or metabolites across individual or different experimental conditions. Our approach in here is that we try to find the relationship between expression values and different gene regulatory networks. And we also come up with a new approach to graph autoencoders, one that is specifically focused on representing the node features rather than the topology of the network. And we show that our approach has practical applications in different scenarios, and we show its representation power by doing a simple imputation task. So some background on graph neural networks is that usually these frameworks try to run a message passing algorithm on the structure of the network. In this message passing algorithm, the information of each node is aggregated with the nodes in its vicinity, and using these aggregate functions and these update functions, they do multiple passes of each layer of this network, and at the end they usually try to minimize the loss function based on the case that they're trying to achieve. These aggregate and update functions are usually differentiable, and different choices of these functions leads to different structures of this network designed for different tasks, such as node classification, graph classification, and etc. Popular examples of these message passing functions are graph convolution network, graph stage, and GraphConv. The message passing formula for which is on the screen, and you can look at it. For our approach, we have two different approaches of indirect approach and the end-to-end approach. In the indirect approach, we train a traditional graph autoencoder to try to reconstruct the adjacency matrix of the network, and we take the embedding matrix, and then again we train a different regression function to reconstruct the expression values of the organism. In the direct approach, we directly feed the expression values and the adjacency matrix to the network, and then we directly try to reconstruct the expression values through the use of this MPNN layer. For this framework, we also introduced our own layer called Fit GraphConv. This layer is specifically focused on representing the features rather than the structure of the network, and we show that it is more powerful than other methods in doing so in our experiments. We use two different datasets for the organisms of E. coli and mouse, and we take the biological networks of transcription factors, protein-protein interaction, and genetic interaction for these for the E. coli, and protein-protein interaction for mouse as the input network, and the expression values as the input features for each node. We run two experiments. In the first experiment, we try to measure the relationship between the network and expression values to establish systematically establish this relationship, and also we run an experiment on the imputation of the randomly missing expression values to showcase the power of our method. In the first experiment, we can see that whenever the expression values and the graph are fed into the network, the performance of the graph autoencoder increases, indicating the clear relationship between the expression values and the structure of the graph. And also you can see the variance explained on the expression values from the embedding matrix, which has also the indication of the clear relationship between expression values and the graph structure. In the second task, we calculate the mean square error of doing 10-fold cross-validation of randomly imputing the missing expression values of E. coli and mouse, and you can see that our introduced layer of message passing, the fourth row, is able to achieve the minimum mean value among all other layers across different networks, indicating the power of this method, and also compared to non-graph-based methods of MLP and magic imputer. So this shows that our method is able to be applied in different scenarios as well in imputation task. And these are my references. Thank you for listening.